Okay guys, in series of lectures based on the complex analysis, uh, that is we are discussing, that is the second module of your curriculum, that is the complex analysis volume 2. Up to the last lecture, I discussed how you can solve the complex integral by the using various methods, and last lecture I started calculus of residue, in which calculus of residue. Up to the last lecture, I discussed what are the singularities and what are the types of the singularities: poles, removable singularity, essential singularity, and then on the last lecture I defined what is the residue at pole. Then I defined that it is denoted by Rs of z equal to A. This is defined by V1. V1 is the coefficient of 1 upon z minus A in the expansion of Lorentz series. So if we open this in form of integral or 1 to pi I integral fz dz, this is V1, this is the residue at pole A. And also I told you about the various methods to find the residue depending upon the types of pole. Simple pole means pole of order 1, pole of various order. There are number of methods which I discussed, and also I took up the number of numerical examples by which all the methods are clear. And last lecture I just stated there is a theorem, that is residue theorem, or it is also known as Cauchy's residue theorem because it is discovered by Cauchy. And on the last lecture, I only stated this and also to an example of this, but its proof is also part of your syllabus. I stated that if we have a closed curve C, and in which number of finite points which are poles on this end, right? Number of poles in this, and Fz is analytic in C except at naturally these poles, and all the points Fz is analytic except these poles. Then this theorem states that integral of Fz over C is defined as 2 pi I into sum of residues at these poles. This was the statement which I stated on the last lecture, that is the residue theorem or Cauchy's residue theorem. A function is analytic in a closed curve C where a finite number of poles are lying, then this integral can also be calculated as, first of all you calculate residue as the given pole, then 2 pi into sum of residue will give you your required integral. First of all, today I will take proof of this theorem, and then I will discuss further about this theorem by taking some numerical example. And there are some different types of complex integral. Those can be solved by using this Cauchy's theorem. First, we take the proof. For taking the proof, let A1, A2, An be poles lying inside given closed curve C. Right? These are the poles. Naturally, the poles means these are the finite points lying inside C at which Fz is not analytic. And now consider small circles C1, C2, Cn having center at A1, A2, An respectively, with a small radii. Now consider a small circle C1, C2, C1 having this small radii inside C. Then Fz is analytic in the region lying between C and these circles C1, C2 and Cn. And so by Cauchy's theorem, because it is a multiply connected region R, that is between C and these, means that region will lie inside C and outside these circles. So the Cauchy's theorem, we have integral C over Z Fz dz equal to integral C1 Fz dz plus integral C2 Fz dz plus so on up to integral Cm Fz dz. We can take this for, you know, that is an application of function of Cauchy's theorem for multiply connected region. We can this one, and because Fz is analytic function, and here if we take A1, because A1 is pole of Fz, then we can take residue at this equal to B1, and by the formula this is coefficient of 1 upon Z1, say in the expansion of Lorentz theorem. So this is 1 upon 2 pi I integral C1 Fz and dz. So from this expression, from this formula of residue, we can write this integral as 2 pi I integral resident of pole at Z equal to A. Similarly, this will be equal to 2 pi I residue at Z equal to 2 pole, and so on, and another integral is similarly 2 pi I residue at Z equal to pole An. Right? That means if you take common 2 pi I, then we get the sum of residues at poles A1, A2, An. And that is your proof of the Cauchy's residue theorem. If a function is analytic in a closed curve, except some finite points, naturally those points will be taken as poles, then integral over the Fz, integral of Fz over this C will be equal to the 2 pi into sum of the residues. Right? That was the Cauchy's residue theorem, which is stated on the last lecture, and that is the simply very simple and very short small proof. Alright, and now by this theorem we can solve a number of complex integral very easily by the help of poles and residue. And there are various types of the integral, those can be solved by using this theorem. In which I think I took up first example on yesterday, and first I will take a second example. This is, if we take an example, numerical example, first I will take, because there are various types of the integral, those can be solved by the help of Cauchy's residue theorem, in which first simply complex integral, as I have done in the last chapter by the help of Cauchy's integral formula, Cauchy's formula for derivative of function, Cauchy's theorem, etc. And second, you can solve also some typical type real integrals by this theorem. based on the sine theta, cos theta, and some also based on the some rational algebraic functions. Those integral can also be solved by the help of Cauchy theorem. So I will take some examples of various types. First, I am taking example of a simple complex integral. Okay, how you can solve these integral by using Cauchy's residue theorem. If we take first example, that is determine the poles of the function and residues at pole fz equal to z square upon z minus 1 square z plus 2, and hence evaluate integral c z square z minus 1 square z plus 2 dz, where c is mod z equal to 3. This is the first numerical example, first sum. There are three parts. First, we have to find pole, second, residue, and then value of this integral. First, if we take solution, that is for poles, you know that put z minus 1 whole square z plus 2 equal to 0. Then we get z equal to 1 is a pole of order 2 and z equal to minus 2 is a simple pole. This is the answer of first part of the question. Poles of the function. There are two poles, z equal to 1 is a pole of order 2 and z equal to minus 2 is a simple pole. Now residue, calculate the residue at z equal to 1, residue, that is residue at this by the formula of limit, as I told you, limit z into 1, z minus 1 of fz. Here fz is z minus 1 whole square and z plus 2. This is this is pole of order 2. There will be the formula of derivative, that is z minus 1 square, first derivative of this, that is z square upon z plus 2 in given, that is because it is a pole of order 2. So here we take the first derivative by the formula z minus 1, 2, 1 square is cancel out, and this is because we have two derivatives, that is the formula. You know that. What is the formula? If z equal to z naught is a pole of order n, then we define the residue as this is limit z tending to a, z equal to z naught, that is z minus z, that is 1 upon n minus 1 factorial, and then nth derivative, n minus 1th derivative of z minus z naught to power n of fz, and n minus 1th derivative with respect to z. This is the formula. So by this formula, this is 1 upon 2 minus 1 factorial, that is first derivative of z minus 1 square upon function this z minus 1 square is cancelled out, and 1 upon factorial 1, that is this. This is z tending to 1, and take differentiation, that is z plus 1 whole square, z plus 2, z square differentiation 2z minus z square into differentiation of z equal to 1. If we substitute the value, that is 3 into 2 6, 6 minus 1 5, 5 will 9, that is the final value of 5 upon 9. This is the this value of residue at pole z equal to 1, because z equal to 1 is a pole of order 2. Simply, if we take the residue z equal to minus 2, that is a simple pole. Simple pole formula is z equal to minus 2, that is limit z tending to minus 2, z plus 2, simply fz means z square, z minus 1 whole square, z plus 2. This is the simple formula. Z plus 2 is cancelled out. If we took the minus 2, that is 4, minus 2 here, that is 9. These are the values of the residue at given pole. Yani means that is the answer of the second part of the question, the residues at given pole. Right? Now, by this theorem, what is the, now that is the third part of the question. Evaluate this integral by using Cauchy's residue theorem. Here C is the circle. You know that this is a circle with center 0, 0, origin, radius 3. This is, if we draw this circle, center origin, radius 3, that is 3 origin. So both are the residue exists, z equal to 1 exists here, z equal to minus 2 exists. Means both poles lying inside the circle. So by residue theorem, integral is equal to the, you know that now by residue theorem, you know that the integral c z square upon z minus 1 whole square z plus 2 dz equal to 2 pi I into sum of residues. Sum of residues means that is 2 pi I into 5 by 9 plus 4 by 9, that is 1. Then finally we get value of this integral is 2 pi. That is your answer of the third part of the question. So this is the way by which you can apply residue theorem and solve any complex integral. Again, I am taking here again another example of ordinary complex integral. Example 2. Question is, evaluate integral c cot z upon z minus I dz, where c is circle mod z equal to 2. Right? This is the other example of complex integral cot z, hyperbolic cot z upon z minus this. This is circle. So first of all, here we have the solution. Here we have this function fz. Fz is cot z, z minus I. This is hyperbolic cos. You know that hyperbolic cot theta can be expressed by the help of exponential function by some standard formula, that is e to power theta, e to power minus theta upon e to power theta minus e to power minus theta, because it is hyperbolic cos upon hyperbolic sine. So this is the formula. By this formula, we break this e to power z plus e to power minus z and e to power z minus e to power z, z minus I. So first of all, we have to find the poles. For pole, we put e to power z denominator is equal to 0. If we solve this, we get e to power z, e to power minus z equal to 0 and z minus I equal to 0. From this, if we solve this, e to power 2z minus 1 equal to 0, from here we get the z equal to 0. This is the first pole, that is the z equal to 0. From here simply z equal to I. So here we have two poles, z equal to 0 and z equal to I. Alright? And both poles lie in this circle, because circle is again center origin, radius 2. If we show this circle, this as radius 2, origin this, 0 is naturally center of circle. I means if we take z equal to I, that is the point 0, 1. 0, 1 is also a point like that on this point on y-axis. This is the another pole. Both poles are lying inside the given circle. So we have to calculate residues at the both poles and then solve this. For this is simple pole. This is for this we have the very simple formula. If we find the residue at z equal to 0, this is simply z equal to 0, and we take function as e to power, that is z equal to I. Z equal to I, take function z minus I cot z upon z minus I. This is the formula. Z minus I is cancelled out. That is, substitute the value z equal to I. This is simply hyperbolic cot I. That is the value of first residue. For second residue, because z equal to 0 is the pole and function is of this type, so we have a method because z equal to 0. This is, and both are the simple pole. Z equal to 0 is a simple pole. So we have also a method of expressing a given function as a rational function, as a ratio of two functions like that. If we take phi z equal to e to power z, e to power minus z upon z minus I whole upon e to power z, e to power minus z. This is a function like that, phi z upon psi z, ratio of two functions. And here we see that z equal to 0 is the pole, so phi 0 is 0, phi 0 is 0, phi 0, but psi dash 0 is not equal to 0. Right? This is the expression. We have a formula. You know that if we have function fz equal to phi z upon psi z, then directly formula residue at z equal to a is phi of a and divided by psi dash of a. This is the direct formula if we have the function in this form. So here z equal to 0 pole. So simply residue at z equal to 0 is phi of 0 upon psi dash of 0. Phi of 0 psi of 0 is not 0, psi of dash. We check this. If we put the value of z equal to 0 here, so this is e to power 0 plus e to power minus 0, 0 minus I. Psi dash 0 means e to power 0 plus e to power minus 0. That is 2. This is simply minus 1 upon I, because 2 and 2 is cancelled out. So that is simply minus 1 upon I. If we multiply it and divide it by I, so that becomes plus I, because in denominator we will get I square, and we know that I square equal to minus 1. So finally we get this. So we have two residue. One is cot I, second is I. Now by Cauchy's residue theorem, the value of given integral is, therefore by residue theorem we have given integral C cot z upon z minus I dz equal to, by formula, 2I into sum of a residue, that is 2 pi I cot I plus I. This is your answer, right? This is the another application of another use of Cauchy residue theorem. So this is the first part. If we have a simple ordinary complex integral, as you have already done in the previous exercises, then those can be solved by using the residue theorem. In second case, if we have the real integrals in form of trigonometrical form, sin theta, cos theta, or algebraic form, rational form, those integrals can also be solved by the help of residue section. like second case may be evaluation of real integrals by, these are known as contour integration. These complex integration, this method, the calculus of residue method, is also known as contour integration. Real integral, if so, first we take up the integral containing trigonometrical functions. Like that, if we have the integral like that, function of sine theta, cos theta, and d theta in C. And here we see basically use as mod z equal to 1, that is unit circle with center 0 and radius 1, and those can be converted into the polar form e to the power I theta, you know that. And also here we know that the formula from trigonometry or algebra, that is sine theta equal to e to the power I theta e to the power minus I theta upon 2i. And also we know that cos theta equal to e to the power I theta plus e to the power minus I theta upon 2. By this formula, we can transform given integral into z complex number, means into same form as I have done in simply complex integral, and then find their poles and respective residues, and by using Cauchy's residue theorem we can solve this. Like if we change this, e to the power iz by this unit circle can be put as z. This is 1 by z, this is 2i. This is again z plus 1 by z, this is 2i. And from here d theta, here dz equal to I e to the power I theta, d theta, that is I e I theta is z, d theta. So from here d theta will be transformed into dz upon iz. That means this integral converted over, because this integral, not see, this is the 0 to 2 pi integral, entire limit of circle around the circumference from 0 to 2 pi. Now this will be changed into complex form, integral c f of this one of z minus z upon 2i, that is z plus 1 by z upon 2, and d theta is equal to dz upon iz. Simply this integral converted into this complex integral. Now this is in a complex integral, so those can be solved by residue theorem, right? By using. So we can solve on this. So first we take a trigonometric example on this. By that can be solved on this, and then I will take up the algebraic example. First I am taking here integral based on trigonometrical functions. Simply that is the example 1 of this series, that use a residue theorem. Evaluate integral 0 to 2 pi d theta upon 5 minus 4 sine theta. Right? This is the problem, trigonometrical problem. Integral 0 to 2 pi and d theta over 5 minus 4 sine theta. So here, for solution, first of all, we have to change this integral into trigonometrical form into the complex form, and then find the poles and residue and use Cauchy's residue theorem and evaluate this. So we take unit circle z equal to 1, and so we know that sine theta equal to ei theta e to the power minus I theta upon 2i, that is z minus 1 by z upon 2i, right? That is z square minus 1 2iz, and d theta I told you that is dz upon iz. Now this integral becomes this 0 to 2 pi, right? D d theta plus 5 minus 4 e to power I theta e to power minus I theta upon 2I by the formula of sin theta, and this becomes integral C. D theta is dz upon Iz. This is 5 minus 4, that is z square minus 1 upon 2Iz. Right? Iz, if we take LCM, Iz is cancelled out from numerator and denominator. Here, that is 2 is also cancelled out. Here we have 5Iz, 5Iz minus 2z square and plus 2. This is the expression. I will get this. Now this integral changes into this form. This is this form, and we can solve this. Take this as a equation 1. Now here we have function 1 upon 5Iz minus 2z square plus 2. So for poles, we put 5Iz minus 2z square plus 2 equal to 0. First of all, calculate this one by, you know that formula, by algebraic, by quadratic expression ax square plus bx plus c equal to 0. Then you know the formula x equal to, you know that formula if expression is ax square plus bx plus c equal to 0. Then x equal to minus b plus minus under root b square minus 4ac upon 2a. This is the formula. By using this formula, this this can be written as by multiplying by minus, that is this minus 2 equal to 0. If we multiply by this, then by this formula, z equal to, by this formula, z equal to minus b means 5i plus minus under root b square, that is minus 25, minus 4ac means plus 16 upon 2a, 2a means 4. This is 5i plus minus 9, minus 9 means 3i upon 4. If we take positive sign, we get 2i plus 5i plus 3i is 4i upon 2. If we take negative, then we have I. I by, this is this, I by 2. These are the two poles here. These are your poles, right? And if we see that here C is unit circle, center origin, radius is 1. So this is not lying because 2i is here outside the circle. But I by 2 is lying on this. Only one pole, I by 2, lies in this. So we take this and find the residue at that pole. This implies that z equal to I by 2 is only pole lying inside C. So calculate residue at z equal to I by 2. Same formula, limit z tending to I by 2, z minus I by 2 and into fz. Fz is this function which we take this fz. If you calculate this, then we get its value. We get its value 1 upon 3i. Simply, this is, if you calculate this, we get this. This is the residue, required residue, and then by Cauchy's residue theorem, what is the value of integral? Therefore, by Cauchy's residue theorem, we get by equation 1 integral I equal to 2 pi I into sum of residue, that is 2 pi I into 1 upon 3i. I is cancelled out. Finally value 2 pi 3. That is your answer of given integral. That is the process by which we can solve a real integral by using a residue theorem. That I have taken the first part, if a function containing trigonometrical functions. And now, in the next lecture, today's lecture is just timing is finishing. In the next lecture, first I will take up another example that is containing trigonometrical function, and then we go through the other features of the application of Cauchy's residue theorem, other real integral, that those are containing some algebraic rational functions. You can solve those type of integral also by the help of Cauchy's residue theorem. Okay, thank you.